All right, we left off the last section. We're talking about ergodic capacity, and at least theoretically there was the hope that if you can code across a fading channel with a large number of independent variations or fades, we can do much better than what we had with uncoded modulation. So I'm going to start with showing you how to actually build a real coding system that can get some of these gains. But first, we need to review channel coding over just the regular AWGN channel. Now, maybe you already covered this in your digital comm class. I certainly teach this, but it's always a little tricky for students, so I'm thinking that a little bit of review is helpful. But if you get bored, feel free to just switch over to the next section. We'll dive right into fading channels, but let's start with AWGN channels. All right, when you want to do coded communication over an AWGN channel, basic blocks are pretty simple. You take your information bit, and the key ingredient is you have a channel coder, which adds basically that redundancy or parity and gets coded bits. We then map them to symbols. We already know how to do that. We transmit it over the channel, and in this case, I'm going to look at a channel without any fading. Then you do what's called the soft symbol demodulation. It's like detection, but you're coming up with not a fixed decision on each symbol, but just a probability embedded in something called log likelihood ratios, and then you give that to the decoder. So, and you've probably already seen this, but if you haven't, I'm going to just walk you through really fast summary of each of these blocks, and let's start with the block for channel coding. So, to understand channel coding, let's understand what is not channel coding, and the opposite of channel coding is uncoded communication, which we've already seen how to do. You take your information bits, and each set of information bits, you map them to a symbol, and that gives you complex symbols, and at the decoder you detect them one symbol at a time. The key idea in coded modulation is that you process information in blocks. So you take a block of information bits, and the channel coding actually adds bits called parity, and that introduces redundancy. So, and the benefit of that is that if some parts of the bits fail, you'll be able to recover them from these extra redundancy bits. Take these coded bits, and then you map them to symbols just like you had before, but with the decoder, you're going to process that whole block together, not processing it one symbol at a time. All right, key parameters that we usually use for block codes. We said it's an NK block code, and K is the number of information bits, and N is the number of total bits, meaning that you could add N minus K parity bits or additional bits. And then you have the code rate is the ratio of the number of information bits to coded bits, which will always be less than 1. So typical values of wireless systems, code block sizes, they can actually even go smaller than this, but often around 100 bits and usually up to about maybe 10,000 bits. After that, it's not that much benefit. You get pretty good performance at 10,000. Code rates go from about 1/3 to about 5/6. Sometimes you're out of that range too, but those are kind of typical numbers that you'll see. And we'll actually build some codes pretty quickly. All right. We've done our channel coding, and we already know how to do symbol mapping, and the channel is easy. So let's talk about the next block, which is this soft symbol demodulation. So setup is this. I have some coded bits, and let's say there are K bits per symbol, like in QPSK there would be 2. And it's getting mapped to a symbol S, and because in the unfaded universe right now, I can just receive that symbol with some noise. In soft symbol demodulation, we're computing something called these LLRs. What is that? Well, in uncoded symbols, remember what you do is you look at the R, your received symbol, and you make what's called a hard decision. I say that a particular symbol is the most likely, or in other words, a particular set of bits for that symbol are the most likely. But what you need to do to get the best performance for coding systems, you make a soft decision. So instead of saying, well, it is this bit or this bit, you assign each bit a probability, or more precisely, a probability ratio, which is this. you say, well, okay, I don't know whether this bit k is 1 or 0. But for each bit, I'm going to assign this ratio. Well, this was the likelihood of that r given it's 1 versus the likelihood that I received the r given that it's 0. And I take that ratio and take the log of that, so hence log likelihood ratio. So this number can be positive or negative. If it's positive, it means that this numerator is larger, meaning bit 1 is more likely. And if it's negative, it means that bit 0 is more likely. And if it's right in between, you have no idea, it's 50-50, that number will be 0. All right, so it's basically same idea of what we're doing in detection, but we're getting this soft probability. All right, that was too much math. Let's just see it's actually not that hard to compute these LLRs. So let's just give a starting example of computing an LLR for QPSK. And again, you probably did this in digital comm. So you have a transmitted symbol, and that means on QPSK, each dimension will be plus or minus some constant, which is related to the symbol energy. And I get a complex, I get that symbol plus some complex noise. And if I want to compute the LLR, this is what I do. Well, let's take a look at bit 0. So bit 0, you can see it's really just being modulated on the real, or what you would call the in-phase axis. So it's 0 means that the real part is here. And if it's 1, the real part is here. And the noise is independent on each. So you could say on the in-phase part, it's like a scalar, like a real value thing, which is that I have that it's the real mapping of that symbol, which is plus or minus this constant A, plus some noise. And remember that if it's complex Gaussian noise n0, each dimension has noise power n0 by 2. All right, this is a real valued Gaussian, so I can compute its likelihood, which is just a Gaussian PDF, and so I put in the variance of n0 by 2 in here, and then it will just be at the mean of this, which will just be SI, and I'll just get that here. Then I substitute these expressions. I want to compute this log likelihood ratio. And when the bit is 1, the symbol is A, so I put that in here. And when the bit is 0, I put the symbol as minus A, and I put that here. And then I take this expression and this expression, and you do some algebra, which I am not going to waste your time with. You get this, which is this basically constant times Ri. Now, don't want to see it algebraically. Here it is just written out, graphed for you. And the idea is super easy to understand. See, if I get a real value, as a higher real value I get, I say it's this log likelihood ratio is increasing. And it's increasing here because remember that the 1 on this case corresponds to the transmitted values here on the real dimension, and the 0 is transmitted here. So if I get 1, it's more likely, and if it's 0, if it's negative, it's less likely that it's 1, and it's more likely that C is 0. And the scaling factor here is related by this constant, which will get a faster slope as the noise is going down. So just remember that actually to compute the LLR, you need not only the R, but you also need an estimate of the noise. And that might also be tricky to get, and we'll talk about that, though, when we talk about equalization. All right, that was a whirlwind tour. I normally go over this really slowly in digital comm. So you can check out that material, which I have, but many other books have this as well. When you have a higher order constellation, you can also compute LLRs, but it's a little trickier because in this case, each dimension, like let's say the in-phase or quadrature phase, has more than 1 bit. For example, in 16 QAM, there are 2 bits encoded in the real part and 2 bits encoded on the imaginary part. So I kind of drew it here like this. So when you want to compute the LLR, what you want to do is kind of take an approximation as follows. You use what's called a total probability. And I say, well, the probability that, say, C, for any C value, well, I do 1, there's 2 bits, C1 and C2. And I want to find the likelihood of bit C1. Well, to find the likelihood, I would technically need to know C2. So I'm just going to average over the possible values of C2. Either C2 is 0 or 1, and then take the average. So, for example, if I want the likelihood log LLR for C1, what I say, well, there's 2-bit positions where C1 is 1. That's this 1, 1, 0, or 1, 1. So So I add those two probabilities on the numerator. And on the denominator are the 2 bits for the other values for C1 equals 0, which are this position and this position. I add these two, and I take the log of that. Now, when you do this, you start getting kind of weird shapes. For example, in the LLR for C1, it looks like this. See, it's more likely that value, it gives a positive value in the center. That's because these two center values correspond to 1, and these two outer values here correspond to 0. Now, on the other one, you get a curve which also looks kind of like this. You'll also see there's an approximation for these. You typically don't have computations of the essence in a lot of decoding problems. You can't do a really complicated approximation. So you often do an approximate LLR, and there's sort of standard approximations for this. This reference, which is actually one of the classic references on what's called bit interleaved coded modulation, is given here, but you can see it in a lot of digital comm books. I won't go over them. All right. Now that we have done our soft symbol demodulation, just a last block for your refresh fast, super fast course in channel decoding. All right, so what happens in channel decoding? We have our information bits. Remember, we're working a whole block at a time. So you transmit K information bits, B, and that generates a code word with N coded bits, and then those get mapped to some symbols, and let's call L, which could be different than N, all right? And then you get a received vector, and what you want to do is estimate the bits, either the information bits or the equivalently the coded bits from that received vector. Now, the way you can do that in principle is basically the same maximum likelihood decoding. For every possible code word I had, I could look at the probability that I got this vector and then pick the code word that had the highest likelihood. But if we're just using with vector quantities. So in principle, it's easy. So let's see, computationally, though, it's a different thing. So ideally, we want to do this. Let's work out the math to what's the function, a little easier function to actually compute this maximum likelihood. So we want to maximize this. That is the same as maximizing this plus a constant. I'll just show you why. We just want to subtract out this constant here, which is the likelihood for the 0 code word. In other words, instead of thinking about it as maximizing the likelihood, I want to maximize the additional likelihood relative to the 0 code word. All right, next thing I'm going to do is I'm going to make a big assumption. And I'm going to assume that every conditional on the coded bits, every received bit is independent. So that means that the probabilities factor as multiplicatively, or the log of the probabilities factor additively. So you can do like this. This is actually not always exactly true. For example, in higher order modulation, these bits wouldn't be independent, but we're just going to do this to make it easier. Now, if I take this and this, I can factor both. So I take the factored version of P of R given C and the factored version of P of R given C equals 0. But remember that the log of the difference is the same as the log of the ratio. So we get this. Now we need one further simplification. So we've simplified it down to maximizing this sum of logarithms. But look at what happens. See, every n, either Cn is 0 or 1. If it's 0, I get log of P of R given Cn is 0 over log of P of R given Cn is 0, which is log of 1, which is 0. On the other hand, if Cn is 1, I just get the probability of C of n equals 1 over the likelihood of Cn is 0, which is none other than the log likelihood ratio. Oh, there should be a Cn times LLR here. All right, so the upshot of this is that when I want to pick the maximum likelihood code word, it is none other than maximizing this weighted sum of LLRs. So I have computed already my LLRs, and I just pick the code word where this sum is maximum. So that sounds actually pretty easy. I just go through every code word and I evaluate this sum because I've already computed my LLRs, and whenever it's maximum, I am done. I picked up maximum likelihood code word. Problem is that this is actually exponentially difficult, and the reason is easy to understand. Remember, you have k bits, so there are actually 2 to the k possible information code words, and for each one of these you would have a code word here, so you actually have to search over an exponentially number of code words if you did a brute force optimization. So actually computing this for an arbitrary code exactly is impossible. So what we want to do, and this is the whole game in coding, is we want to somehow find computationally tractable codes that you can either compute this or compute this approximately well enough, but still have good performance. And that brings us to kind of what you'd say is been a whole search in coding theory since Shannon began. So Shannon published his theoretical results all the way back to 1948, and there was a continued amount of work after this, though, to get actual codes that could perform as well as the theory predicted. Sort of the first codes came out pretty early, like the Hamming code, and that's always one I use when I teach channel coding because it's really easy to understand and make some calculations by hand. But the most common first real commercial uses of coding use what are called Reed-Solomon codes, and they're basically algebraic constructions. We're not going to talk about them here, but they actually dated back to the 60s and were even used in some things like the space program in the 70s, and it showed up in CD players, if you remember what a CD player looks like. But the workhorse for industry up until about the mid-90s were what are called convolutional codes, which I do cover as well in the digital communication class, and I'm going to give you a really fast overview of that. And they actually can get within about 3 to 4 dB of capacity. In the mid-90s or early 90s, there was a real breakthrough, though, and got a remarkable performance for something called turbo codes. And these actually got within a fraction of dB of capacity. I'm just going to show you a couple of slides just to give you a high-level conception of them. And they became widely used in 3G and 4G systems. And then finally, LDPC codes, which are also based on iterative decoding, became used in 5G systems. And I'll show you actually how to encode all of these things in MATLAB pretty soon. So let's just quick review about convolutional codes. And this is the high-level summary. So you take your data basically through parallel streams of FI, what you could call like finite impulse response filters, but everything working in modulo 2 arithmetic. So for example, what I do here in the right is a very simple convolutional code, which is a rate half code. So for every input bit, I pass it on to a shift register and I get 2 output bits, C1 and C2. And all this picture means is that C1 is just the modulo 2 addition of the last 3 bits, and C2 is the modulo 2 addition of bit t and t minus 2. Now remember, it's modulo 2, so if this was like 1, 0, 1, 1 plus 0 plus 1 in modulo 2 is 0, all right? So you still get this bit. So you get, for every input bit, 2 bits, output bits, hence rate 1/2. Now, the benefit of this is easy to implement, and you can decode it kind of by a kind of dynamic programming method, iteratively working back from the code. All right, and that classical algorithm to do that is called the Viterbi algorithm, named after Viterbi, who actually went on to found Qualcomm. So very, very productive career and contributions to wireless. All right, and again, go back to your digital QM class for more info on that, but just give you a little bit of the performance. So this I took from Proagus's book. Proagus's book is really encyclopedic. It has kind of like every code and gives lots of different performance graphs if you want to check it out. And here you see the performance of this, and you can get these nice sharp decreases here. Typical constraint length that you need. So constraint length is the length of that filter. And the complexity grows with the constraint length, but usually a constraint length of 7 or 9 is usually enough to get good performance. And they perform very well. As you can see here, you need about an EBNO in this case of a rate half code, somewhere in the order of like 4 or 5 dB, depending on the error rate that you want. Now, what's great in MATLAB is that, so if you, I sometimes have students write a Viterbi decoder from scratch in digital comm, but it's actually a lot of work. MATLAB is amazing. It has like all sorts of codes built in, so you can write encoders and decoders in just a few lines. Here's an example. You can go to the demo. You can get all the details, but you can create a graph like this, which is the block error rate as a function of the EBNO. And you just do this. You take your bits, you generate them, and you literally call one line, which is an encoder, to encode the bits. This is an object which you construct with the graph you want. Then you modulate it, again, one line, add noise, and then you can use this Comm demod function here to compute the LLRs, and then you can run the Viterbi decoder. In this case, it gives you some tail bits that you have to remove. Little minor thing. But there you have it. In about 10 lines, you have a coder and decoder simulated in MATLAB. It's a really amazing tool. It works actually quite fast, and you can easily generate thousands quickly and get this kind of graph. So as I was saying, that was convolutional codes were kind of the workhorse of industry throughout the 70s and 80s. But in the early 90s, there was a real revolution in coding through an amazing discovery called turbo codes. And they actually build on convolutional codes. So this is the structure. You have your information bits, and you send them out. So they're kind of like what you would call a systematic code, because they includes the information bits. But you have also two sets of parity bits. The first bit is generated by taking the just a regular convolutional code. It's actually kind of an IAR version of a convolutional code, but basically a convolutional code. And that gives you the first set of parity bits. And then you do what's called an interleaver, which just scrambles the bits. And then you pass that through another convolutional code, or even the same convolutional code if you like. And that gives you an output, second output. So taken together, you have n bits, and then you have these two n bits from each of these. And this gives you basically a rate 1/3 code. And this code, which is the right decoding algorithm, which I'll show you, actually got within a fraction of a dB. So how does the decoding work? The decoding uses a very clever idea called message passing. And maybe I'm going to go back to my graph to give you an idea. So if imagine I didn't have these parity bits, P2. I just had the output bits and the input bits. Then it would be like a regular convolutional code, and I could use the Viterbi algorithm. But I use a soft version of the Viterbi algorithm, which just says that, okay, I'm not going to make a hard decision, but I'm going to assign a probability of my information bits based on what I learned from these parity bits. But now I haven't used the second parity bits. So I go and take those bits, that information, and I combine it with the observations on the parity bits, and get a new set of updated probabilities for my information bits. And then I keep on alternating back and forth. Hence, turbo, kind of like a turbo engine that it takes its output and feeds it back in as fuel to keep it going. This remarkably achieved incredible performance, and this was really one of the most significant papers of that year. This is one graph. It's actually taken from Lynn and Costello's excellent book on coding, so you can check that out. But here is the Shannon capacity for BPSK, and it's just within a fraction of that dB. Nothing like this kind of performance had been observed before. And in fact, this led to what you could call a whole turbo revolution. People were using turbo codes and turbo ideas of decoding in all sorts of parts, like channel estimation. It led to all sorts of interesting papers, and but from a commercial standpoint, these codes were very quickly adopted into 3G and 4G systems, and so you're using them on your phone today. Very similar type of iterative coding technique is done by what's called low-density parity check codes, and they're built on what's called a bipartite graph. So remember, from block coding, the code is determined by something called a parity check matrix. When you multiply the received vector by this matrix, it's 0 when you have a valid code word. So what you do is you have one node in this graph, every parity check bit, and one other set of nodes for each coded bit. And this graph encodes their relations. And then again, you can do an iterative message passing type method to actually decode this. And this too could get very close to Shannon capacity. And in fact, later it was shown that you could even achieve the Shannon capacity through a specific type of graph structure known as a spatially coupled graph. I'm not going to have a chance to go over any of this, unfortunately. It's a beautiful theory about what are called graphical models, if you want to explore it. And interestingly, some of this stuff about spatially coupled graphs are very similar to the codes that you will see in the new radio standard, where they have a concept of a base graph that is lifted. Okay, that wraps up what I'm going to say about coding and talking about the new radio code. I'm actually going to show you, or going through this exercise, you can actually use MATLAB's 5G toolbox to actually encode and decode using really state-of-the-art LDPC codes that are in the 5G standard. You just give this what's called base graph and a lifting factor, and then just call an encoder and call a decoder, and you will be at your own fingers on MATLAB be able to get the super powerful use of these codes over an AWGN channel. So try that out, and once you get your AWGN channel, go to the next section and we will talk about how to extend this to fading channels.